Picture a stunt driver staring at a 40-foot canyon. The engine is revving. The ramp is ready. They know their speed at takeoff, but here's the question. Will the car actually make it to the other side? The answer isn't luck. It's physics, specifically the power of kinematic equations. Today, we're going to unpack the real toolkit for predicting motion. You'll see how motion diagrams tell the hidden story of velocity and acceleration. You'll master the three fundamental kinematic equations that govern constant acceleration. And you'll learn how to use them to solve problems step by step like a physics detective. Our goal is simple but powerful: to describe motion, position, velocity, and acceleration using motion diagrams and kinematic equations. So, let's begin. Motion diagrams are like freeze-frame photographs of movement. Imagine taking snapshots every second as a car moves along a road. Each frame marks the car's position. Add red arrows to show velocity and purple arrows to show acceleration. Instantly, you've turned a picture into a physics story. The spacing of those snapshots tells us everything. Equal spacing means constant velocity, increasing spacing means acceleration forward, and decreasing spacing means acceleration against the motion. Let's break it down with 3 examples. First, constant velocity, equal spacing, equal red arrows, no acceleration arrows. Second, accelerating forward, positions spread farther apart, velocity arrows grow longer, and purple arrows point in the same direction. Third, decelerating, positions crowd closer together, velocity arrows shrink, and purple arrows point the opposite way. But here's the case that matters most: constant acceleration. This is the foundation of nearly all beginner physics problems. Why? Because under gravity near Earth's surface, acceleration is constant, about 10 meters per second squared downward. Sometimes we use the precise value 9.8, but either way, that steady pull of gravity makes motion beautifully predictable. And that's where the kinematic equations come in. There are 3 of them, and together they're a complete toolkit. First, velocity as a function of time. V equals V naught plus AT. Second, position as a function of time. X equals X naught plus V naught T plus 1/2 AT squared. Third, velocity as a function of position. V squared equals V naught squared plus 2 A delta X. Here's the trick. Each equation ties together 4 variables: position, velocity, acceleration, and time. Know 3, and you can solve for the 4th. That's the golden rule. Let's put it to work. Suppose a ball is thrown upward at 15 meters per second. How high will it go? At the very top, its velocity becomes 0. We know the initial velocity, the final velocity, and the acceleration due to gravity. Which equation fits? The third one. Plugging in the values, 0 equals 15 squared plus 2 times -10 times delta x. Solve, and delta x comes out to about 11.25 meters. The ball climbs roughly 11 meters before gravity stops it. Notice the structure there? That's the problem-solving strategy you'll want every time. First, read carefully and identify the givens. Second, pick a coordinate system and define positive direction. Third, list what's known and unknown. Fourth, choose the right equation. Fifth, solve algebraically before throwing in numbers. Sixth, check if your answer makes sense. Follow those steps, and you'll dodge nearly all common mistakes. Graphs make this even more powerful. Position time graphs curve into parabolas under constant acceleration. Velocity time graphs become straight lines. The slope of position time is velocity. The slope of velocity time is acceleration. And the area under a velocity time graph gives displacement. Graphs aren't just pictures, they're cross-checks on your math. So let's recap. Motion diagrams reveal how position, velocity, and acceleration play together. The three kinematic equations let us predict motion when acceleration is constant. A systematic approach keeps our problem-solving clean, and graphs tie the whole story together visually and mathematically. In the next video, we'll explore reference frames and relative motion. How can two observers see the same motion differently? The answers reveal deeper truths about how motion works in our universe. For now, remember this: when acceleration is constant, motion is predictable. These equations are your key. Practice them, use them, and you'll be able to unlock the future of any motion problem.